to make sure to record it. Okay. Let's jump in. Any questions so far about the material we talked about? So if I remember correctly, before 2 weeks ago, we now, I think, established final rules. And then, I'm sorry? Feynman. Oh. I should be careful. I heard that I should be careful. Because am I writing Feynman correctly now? Okay. I feel weird.
And double N? I mean,
take a grain of salt with a grain of salt. Feynman diagram and then rules. Okay, so we did the explicit algebraic computation. So again, let's take the example of this thing, Yukawa theory. And then, for instance, as an example process, we looked at, what we did look at? So we looked at Nn goes to Nn, where, remember, I marked the particle produced by the psi n, and then particle produced by this phi, probably. So there are two Feynman diagrams, okay? Not the weak diagram, but Feynman diagram in the momentum space. So one was this, okay? So there's a charge fluid, therefore momentum fluid is a parallel. So there's a P1, P2, P3, P4, P2, so there's N coming in, there's ion, exchange in the middle. And then if I assign Q, momentum transfer, so there was 2 comes out, 1 comes in, so which means that this should be equal to P1 minus P2. And then there was another diagram. So let me see if I can do it. This cross diagram. So everything is the same except you exchange the P1, P2, right? So that was P1, P2. Therefore, momentum transfer is literally replacing P1. Oh, P3. Nobody complained. Yeah, good. P3. So this is now P2 minus P3. And then, before I write down this amplitude, recall that the S matrix, or S operator, can be expanded as this. This is not a small parameter expansion, this is the exact definition. So nothing happens, something happened, right? And then, we can write this as delta IF. So nothing happens, I, and then so there's always momentum conserving delta function, and then the rest we define as invariant amplitude. Okay, Feynman invariant amplitude. So the Feynman rules for this guy, not the T, although I discussed the both. So Feynman rules for this guy was that with each vertex, you assign minus I times G. And then, not just that, you assign the momentum such that momentum conservation is enforced. Okay? So once you do that properly, then your Feynman rule becomes much simpler. External legs for scalar, nothing, 1, and then there's a propagator in the middle. You just put the propagator. So with that, right? So for instance, for the internal line, you put the propagator. Okay, so then we can write down the amplitude in this example. So we are writing a process which is for Nn goes to Nn, and then there are 2 contributions. So one contribution, we have computed it, okay? So we have computed it, so let me just write it down. So that's the answer we got. Optimize probably. So what was this delta? Delta was so Q square in the first example, P1 minus P3 square. And so we computed it in the center of momentum frame. So if we compute this in the center of momentum frame, what we got was this 1 minus cosine theta, and then we call that to be minus momentum transfer squared. So this P is magnitude over 3 momentum that gets exchanged along this line. And then this was literally crossed, meaning delta C was another example, P2 minus P3 squared, basically the same, 1 plus cosine squared, and then we call that to be cross momentum transfer. And that was the answer. To gain a insight, I'm reviewing this because we will build up on top of this. To gain an extra insight on top of this, this is a completely spatial momentum, right? This had both information about the size as well as the angle. So that's literally just telling you what is the 3 momenta which gets exchanged right, in that process. So to gain a extra insight in the position space picture, we have done the Fourier transform. Okay? So basically we Fourier transform this to this. So if you do it, what we saw was that this amplitude, okay, goes like basically you call it potential. There's a G square, and then what we had was a 1 over 2, I forgot 2 or not, minus n, and then cross. Okay, so that was about the discussion we had for pi r. I mean, this was 4 pi r, which is correct up to 2 pi, exactly. Okay? And then we talked about the physical meaning of that. So that's sort of a quick wrap up what we talked about. Okay? Today we will build up on top of this. So the main topic I want to discuss today is crossing property and then CPT values. But this is a good thing to have already. So to do that, to build up the discussion, I want to talk about another process quickly. Okay? And that process I want to talk about is, instead of NN, I want to talk about NN bar goes to NN bar. The anti-nuclear. So what are the Feynman diagrams? It's almost the same. So one goes in like that, so it's parallel to the momentum direction, that's N. And the other one, I reverse the arrow. Okay? So in this case, momentum direction and the charge fluid direction are opposite. So that's N bar. So the first diagram is identical. There's a second diagram. Can I do? Let's see. Does that work? No, that doesn't work. That doesn't work. Another diagram I want to talk about is this. It's not that nice. Okay? Coming in, out, in. So this is again parallel with the momentum, so N, it's opposite, and bar. This is parallel, and this is opposite, and bar. And pion gets exchanged here. So pion gets exchanged that way, which we will make precise what that means, and pion gets exchanged this way. Okay, so now, what are the differences, first of all? Well, it's different, because N bar versus N. In particular, now your answer should not naively respect, the fact that if you exchange the P1, P2, you get the same answer, right? You shouldn't get that. Here, those were identical particles, obviously, by boson statistics. If you do that, your answer should respect that statistics. Okay? We talked about that last time. Here, obviously, they are not identical particle, and there's no reason you respect that answer. Okay? Let's write down the amplitude for this. So again, assign P1, P2. This is literally the same. P1 minus P2. No. P3 P3, 1 minus 3 squared. Just that. Okay, and then this is P3, P4. What about this? So here, Q is P1 plus P2. So they meet. I'm going to write down the answer for that, okay, using this final rule. We just reminded ourselves. And then discuss a bit of physics before I start discussing the general meaning of a crossing property. So let's try to write down the amplitude. So minus RE squared, because there are two vertices each. So this is a second order perturbation theory. The first one is basically the same, right? So that is P1 minus P3 squared. And the mass for the pi is this. Okay? And then what about the second one? The second one, alright, so that's the answer. Now, let's talk about what we already know. So this you already know. So that part is already related to delta square, momentum transfer, as we just talked about. Okay? What about this? So let's go to the center of mass frame to check what they are. So go to the center of momentum frame. To do that, P1 I choose as an E, and then P E hat, P1, P2, minus directions. That's the definition of the center of momentum frame. So if I compute that thing, so P1 plus P2 squared, what is that? So if you added up this, what do you get? P1 plus E2 and 0. And this is nothing but ET squared. Total energy, right? So this is the total energy of the collision and square. So in this case, we get just ET squared. So the difference is that in this case, if you recall, let me just quickly write it down. P1 minus P3, what was that? So that was, if you're using the same energy, that was a 0, and then it was a P, E hat minus E hat prime, where E hat prime is the deflected angle, okay? This is the momentum direction after. So if you look at these two, try to understand the difference in physics, this diagram, where momentum transfer appear, intermediate line appear as this shape. If you go to the center of momentum frame, you only get spatial component. So only the 3 momentum you get. On the other hand, in this example, if you go to the center of momentum frame, you only get a temporal or energy component. Okay? So far I'm literally just pointing out the difference. Now, where does this difference come from? What does this mean in terms of difference in physics? So to check that, let's actually do the following experiment. So suppose I'm following a given time slice. So I'm just now following some time slice. So what I'm trying to say here is the following. So you have a N and N bar. If you follow this process time by time, there is no time where these two particles actually merge each other and disappear. Okay, you always have that. You might say, is that because of the direction I follow? You can try to do another time slicing like that. For instance, okay, this is more radical. Let's do it. So, okay, here N and N are separate, right? Here N and N are separate, and so on and so forth. So at some point, at some time, you might see the phenomena that N split into N and pi. And then another time, you might see that that pi merges with N bar. But in this process, where there's a pion exchange, in this vertical level, vertical manner, there's no time that N and N bar actually merge and they're turning into completely different particle. That's the same thing here. So if you do the time slicing, at some point, you have to find a time where n and n are actually merged, it disappears, and then turning into a completely different particle until that particle turns back to n and n bar. So these types of phenomena, where you just have n and n all the way, but there's some interaction exchange that keeps happening. There, the characteristic of those processes is this momentum transfer, as we saw in this example. But in this n bar, nuclear and anti-nuclear process, the second contribution is qualitatively different from the first. In the sense that there, two particles meet each other, disappear, and then turning into completely into some different particle, and that is characterized by somehow the center of momentum frame total energy, rather than the momentum transfer. Okay? Alright, so now we're gonna go one more step beyond. That one more step beyond is the following. So now if you look at the amplitude, okay, I have to write down the amplitude a bit. Now let me actually rewrite this in terms of this. Okay? Now, one qualitative difference, important difference, is the following. So here, previously, that diagram, here the poles on imaginary axis. Right? So if you recall, in that case, there was a pole here and there, and then we had to do the integral. Depending on the side of that, either you have to close up or down, right? That's what we did. And then we did that Fourier transform to get this, you call it potential. That's what we did. On the other hand, now if you look at this, you get an amplitude that looks like et squared minus m squared, 1, proportional to this. Okay? And let me put IET, just make sure. In this case, you see that the pole is on the real axis. Okay? So, for instance, the same complex plane diagram. Now, because of IET, you can check that originally you had a plus minus plus minus m, but it will shift a little bit downward, then shift to this guy a bit upward. So the pole will appear on the real axis, but once again, for computational reason, or just to maintain the causality automatically, this item will just shift a little bit in towards the negative and positive imaginary direction. Okay? So, the phenomena that I explained to you. One, you never have a moment in the time that two particles completely merge and disappear, versus that actually happened. A captured by these two facts that I just mentioned, but again, this gets translated into the fact that in one case, poles or singularities lie on the imaginary axis versus singularity lies on the real axis. Okay? So now we go one more step. So we have done the Fourier transform to get this, you call it potential. You might ask, what about it here, right? What happened if you do the now Fourier transform? Now, the difference is that in this example, in this case, it is only temporal component that you have, versus you only had a spatial component you have here. So for this case, since you only have a spatial component, it was right to do that the correct Fourier transformation is only in this 3 direction. Here, obviously, you want to do it in the temporal direction to see what the physics is. Okay? So let's actually do it, which should be great. So if we just do the Fourier transform of this, what would you get? Well, you get et to get a function of time, right? So if you do that, you see that in order to which pole you have to pick. In other words, where do you have to close the contour? So in order to have a convergent exponential, so this suggests that imaginary part of the E has to be positive, negative, negative. Okay, that tells me that I'm gonna pick this contour. Okay? Therefore, I'm actually getting contribution from the positive pole. which is more physical pole. Okay? In other words, it will be weird to pick up the pole where energy is a minus of something, right? So in this case, you're gonna get energy equal to positive mass. So it's a physical pole. So if you do it, then using the residue theorem, so this denominator is like Et plus m, Et minus m. And here you should get plus I epsilon minus epsilon in detail if you work it out. Okay? So residue theorem suggests that this you get 2m, roughly speaking. And then here you will get e to the minus I m t. That's all you get. Up to whatever, 2 pi. Now, what's the difference? Remember here, if you do the Fourier transform, you get a potential. So you get an action in distance, right? So what happens? What sort of an effect do you feel as a function of r away from the distance between the two particles? Here, what does this describe? This is oscillatory thing. This is time evolution, which means that this is literally free propagation of a particle with mass m. Okay? Think about the quantum mechanics. This is literally how time evolution works. This is the exact time evolution for a particle who has a mass m, e to the minus IET, and then you have a free propagation. Does that make sense? Yes. According to the diagram I just erased, that channel was characterized by the fact that two particles merge each other and fuse to produce a particle, and then it will have a free propagation for a while until it has to decay back. Okay? So that's the difference. Now, why am I talking about this? Because, well, first of all, this is a physics. You want to understand what's going on, and so on and so forth. But eventually, we will talk about the case where there's a single amplitude as a function of a momentum, which I will make it much more precise. The single amplitude of a momentum can describe different processes at once. Okay, so that's where we are heading. So we just talked about the one process, which was an n to nn. We just talked about nn bar go to nn bar. And even not worrying about this fancy crossing symmetry and so on, you should be able to understand the physics. You can compute it, try to understand what the meaning of the pole, whether it is an imaginary axis versus a real axis. What does that mean to have just exponential fall off versus actually, e to the I something? So you should be able to understand the physical meaning of that. Okay? So connect structure, singularity, the actual feature. What else can we talk about? What other processes does Yukawa theory can provide? We can also talk about n pi goes to n pi. Right? So let's just quickly talk about only the diagrams, and then we'll just move on. What kind of diagram do you have here? So, for instance, you will have time goes that way. So pi n, pi n. Okay? And then there will be also a crossing diagram. Oops. This also describes that n pi goes to n pi. Okay, in principle, you should be able to compute it. What else? The last example. We can also talk about n, let's see, I have to be careful. N bar goes to pi pi. So what are the diagrams? You have this diagram. N bar goes to pi, goes to pi. And then there will be crossing diagram. Okay? This like that. Okay? So that's sort of physical processes, and now you should be able to compute this amplitude and understand the singularity structure, and then understand what that means in terms of physical feature. Whether it describes free propagation. Remember, free propagation comes from this real pole. Okay? Action at distance came from pole on the imaginary axis. Okay. Good. So that's what this Yukawa theory can provide. Now let's actually talk about somewhat abstract thing known as crossing property. And sometimes called crossing symmetry. But this is not quite a symmetry in a sense that we talked about. Like there's a symmetry of a theory, there's a Noether's current, the selection rules. No, that's not that symmetry. So as you will see, this is just a property. So to do this, I want to set up the following picture. So there's just some block, something happens. Let's just talk about 2 to 2. And I will take a convention that every charge fluid goes towards the block, like this. Okay? And then I will take a convention that all momentum goes towards the blob also. Okay? And whatever this is, this will have an associated amplitude. Okay? Just like what we just talked about. Okay? This will have an associated amplitude. Now, the reason why I want to set up things like this is because I want to use a single object to talk about different processes. Okay? So, for instance, if I read time as flowing from right to the left, so I'm reading this way, then for particle 1 and 2, the direction of a charge is along the momentum direction of momentum. On the other hand, for 3 and 4, it's opposite. You do not have to read it this way. So naively, I will make more precise. This process may correspond to 1 and 2 particle going into not particle 3 and 4, but antiparticle 3 and antiparticle 4. So they may describe 3 bar plus 4 bar. That's this exercise. What about if I read the time flowing from the top to bottom? So now I have a 1 and 3 particle turning into 2 bar, 4 bar. So let me write. Okay, so let's do one more. I cannot do because now I have to take this and then let the other go in. Okay, so boom happened, and then it can also describe 1 and 4, and then reading the other 2 coming out. So 2 bar, 3 bar. Then include this. And then many other stuff you can play with. Like 2, 3. Anyway, you know what I'm talking about. Pick 2 as it is, reverse the other 2 to get this. So something happens, entire dynamical information is stored in this block. So that dynamical information is precisely what amplitude, right? That depends on the theory. What kind of singularity, what kind of analytic structure it gets. Okay? So that's all encoded in here. But at least from this picture you can interpret that this thing is capable of describing many different kinds of processes. Okay, so let's now be more precise what I mean by that. So to understand this, let's recall the following facts. So for scalar field, for instance, I have a 5x, and then we have this structure. Let me take a complex field for the general. So, therefore, from this, we can understand the following. First, I want to have a block here. There's something fluid going into this way with the momentum assigned parallel to the charged fluid. This is like, I had some particle state, let's say n, with the momentum p, and then I'm using this operator and turning into block, right? That's sort of the picture. Okay? What that means is that I'm going to use a annihilation part to destroy the particle state turning into block state. Okay? So here, I'm going to use alpha part. In fact, you can compute this explicitly and actually equal sign, but you should get e to the minus ip dot x. Okay? If this is x. Second time, let's talk about the other case. So let me intentionally draw this way. So you actually charge fluid going in, you want to take out something out of the block into a state. So what it means is that I'm gonna have a n-bar state with a momentum p, but somehow from this operator starting from the block. That's what I'm talking about. If you like, you can just use this as a vacuum, but derivation should still go through. In this case, what you're doing is that you're going to use a creation operator to produce antiparticle, and it stayed at antiparticle state as you flew out. So what it means is that here, this time, you're going to use a creation operator for antiparticle. Okay? And in fact, again, exactly the same reason, you get this. Now, this will have a far-reaching consequences from now, so you really want to understand what I'm saying here. Okay? So there's a block, whether you interpret that as a, something going into the block or something coming out of the block, I'm saying that analytic level, the expression level, this is how you think about it. Okay? Now, you may notice one feature. What is that feature? So these are related by P mu going into minus P. We will be dealing with now a function of external momenta. Okay? We will be dealing with a function of momenta. We were dealing with a function of momenta. And then what I'm saying is that whether you use P versus minus P, it changes the meaning. It changes from incoming particle to outgoing antiparticle. So as you change P, some assigned momentum P, and then instead you just swap the sign, then this was incoming particle that turns into outgoing antiparticle. Okay, so now I'm gonna make one more statement related to this. So in this convention that I'm taking here, obviously you have to make sure that P1, P2, P3, P4 add up to 0. So that's basically energy momentum conservation statement. Suppose I had this P1 and then P1. I'm being intentionally super detailed because you can get confused. So suppose somebody hand you this thing, okay? Somebody just hand you this thing, and then whoever gave you, he or she gave this data, you found out that the E1, E2 are positive. Okay? And then that person also told you that whatever this process is 2 turning into another 2 process. What that means is the following. What that means is that the E3 and E4 has to be negative to satisfy this condition. Right? Otherwise, energy will not be conserved to 0 in this convention.
Can E3 be positive and E4 be larger than negative?
But I told you that this process, okay, good, that's a logical possibility, but that's why I said that there's one extra statement. This process corresponds to 2 particles turning into another 2 particle. Indeed, E1 plus E2 plus E3 plus E4 has to be 0, and if you know that two energies are positive, at least you know that at least one of them should be negative, right? To satisfy this condition. What I'm trying to say now is the following. Suppose somebody hand you this, and you notice that one of the momentum assignments is such a way that it is a negative energy, the negative Zeroth component. You might say, what kind of crap is this? It cannot be possible. The way you understand that is the following. Correct interpretation of this feature, if I say in word and then I'm going to be precise, is that you now understand that the momentum corresponding with the negative zeroth component corresponds to actually going the other way around than the arrow itself. So why is that? So let me clarify that point. And then I will make a contact with this point. So what that means is the following. So suppose that you have this, so you have a P dot X, right? And then this will have a ET minus PX, right? If this for momentum P is such that this is negative, you can reinterpret this as minus E minus T. What it means is that now I am talking about positive energy, so sensible energy state. But now the direction of the time is reversed compared to whatever the assignment of the diagram. So when we first draw this diagram, when I was telling you the convention, I'm taking a single time flow, and then everybody going in, everybody going like that, right? But then if the sum of the momentum has a negative zeroth component, the correct interpretation is obviously to take the positive energy direction, which means that for that arrow, for that external leg, time flow is reversed. So, for instance, in this example, instead of saying that, time clicking and going that way, time goes backwards, so it's actually coming out. Therefore, in this convention, which one comes out, which one comes in is already determined once you look at the zeroth component of that moment. Okay? Good? So that's energy component. Is that clear? Momentum with a negative component, actually time flows backwards, it's coming out. Now, let's continue to discuss what about the momentum direction. Suppose you had a P1, P2, such that they're actually going towards the vertex, interaction block. Okay? Once again, in order to satisfy the momentum conservation, this guy, I will assign going also towards the vertex, right? But then, really the momentum conservation is saying this. So P1, P2, again, imagine they're going towards together like that, is equal to minus P3 minus P4. So this is how you want to read the momentum conservation. Something goes in, the same amount comes out. Right? That means that minus P3 is along the same direction as the initial momentum. Minus P4 also sort of move towards the same direction of initial momentum. So something comes in, one P1, P2, you want to see something other two comes out. Okay? So therefore, what that tells you is that if you had some ith momentum whose zeroth component is negative, okay, then actual physical momentum for this guy is minus Pi. This is the physical momentum that he captures. Okay? Minus E is actual positive energy state. Minus momentum direction is actually propagation direction of that particle. Okay? So I took the time to explain this. So whenever you see one of the momentum with the negative energy, the correct meaning of that is that the actual physical momentum corresponds to minus of that momentum. Now let's go back to this. Yes?
And how does this go to them being particles in line?
Antiparticle means that because if I take again the same convention as the charge flow always inward, this discussion only tells you that the momentum actually going backward. And I told you that this is related to this. Our convention for the drawing was that if the direction of a charge flow is opposite to the momentum flow, that was for the anti-particle. And that was this exercise. Okay? So you see that what goes with the charge flow is associated with a particle. It comes with either the minus ITX. If I wanted to look at it the other way around, so there's something going towards the vertex, but something coming out. If you do this check, again, you get now either I plus IPX, so P exchange to minus P. When you flip the P, what was particle goes into particle. And I just explained to you why this is the correct thing that you should expect to see, but just based on the physical explanation. All right, good. So this is the preparation to now state the crossing part. If you have any question, feel free. Okay, so now here is my now notation. So if I had a pi component 0 is positive, I will denote it as pi plus, and then if I have jth momenta but whose 0th component is negative, I will denote that as minus. Okay. So with that convention, squeeze in loop there. Okay. So let me write this amplitude. So this amplitude will be written as E with a P1 plus, P2 plus, or P3 minus, P4 minus, right? In other words, in this corresponds to the case where the 0th component of P3, P4 are negative. And I just explained to you that the correct physical momenta associated with the 3 and 4 is now P1, P2 is as it is. I should use P3 and P4. Okay? Okay, let's finish this exercise. So this corresponds to P1. Let me just use this convention already. P3, P2 should be minus. P3 minus P4. Okay, so this is the physical region. And this, therefore, corresponds to P1 minus P2 minus P3 or plus P4. So far, it's mostly notation, but with the physics understanding that I just explained. Okay. Now, what's the real statement about the crossing property? Now, here I'm talking about basically, so for a QFT with only scalars, which is the case that we are dealing with. It is Yukawa theory, for instance, as we talked about. The amplitude is only a function of wow, so what are the candidates? Let's again talk about 2 to 2. So I'm still talking about 2 to 2. Remember, this is a function of external momentum, but it should be Lorentz invariant function. Okay? Hence, Lorentz invariant amplitude. What are the possible arguments of this function? Suppose I have a 2 to 2, so I have a 4 momenta. So you have a P1 square, P2 square as a Lorentz contraction, P3 square, P4 square. Okay, these are acceptable Lorentz invariant arguments. What else? I can have Pi, Pj with all kinds of choices, right? 1, 2, 1, 3, and so on and so forth. Or I can recombine this as follows. I can combine P1, P2 square. So that we will call S. And then we can combine 1, 3. We will call that to be T. And then I can combine 1 and 4. We can call that to a U. So you can convince yourself that this encode all these possibilities, right? 1 square, 2 square, 3 square, 4 square, 1, 2, 1, 3, 1, 4. You might say, what about 2, 3? So for instance, this is equal to, by momentum conservation, 3 plus 4. So here we go, you get 3, 4 in a product. And again, by momentum conservation, this is equal to this. So again, you get the 2.4. So here you get 3.2. Okay?
So it equals the on-shell condition, right?
Yeah, because these are external lengths. They have to satisfy the momentum conservation and on-shell condition. Yes.
So effectively, the P1 square, P2 square are not the argument in the argument of uncertainty.
Sorry, this is a function who has something like this as a part of its functional form.
Yeah, but Pi square is just mass square.
True. Yes. Right. So good. You will see, but we will take this as a function, amplitude as a function of this, and then we will start exploring different regions in the complex plane and momentum. And you can go to the on-shell regime where this becomes not a parameter but just a number.
Then there is some difference between variables, number of variables.
Number of variables. What do you mean? You mean this and that?
Yeah.
You mean the counting wise?
Yeah.
So here, when I say this, good. So let me clarify. For scalar field theory, we are looking for what are the possible Lorentz invariant made out of the momentum, right? Before worrying about the on-shell, this is the fullest claim.
Yeah.
Okay? If you go to the on-shell, something becomes a pure number because this is equal to just the mass of that particle. Okay? And this can be viewed as a function of still this. Again, if I don't go to the on-shell point, this is generic function of this. And then we can take that function, go to the different regimes in the particle, the momentum value. That's the game we're doing.
I think he's talking about this. If we do not impose the on-shell condition, then we cannot say that A is a function, only function of the STU. I mean, if we give up the on-shell condition, then we have to introduce more variable to express A in terms of P1, P2.
So you mean this is a smaller set than this, as you're saying?
Yes. Yeah. If we impose on-shell condition, then two sets are equivalent.
Yes.
But if we give up the on-shell condition,
Yes.
then two are different.
Yeah, say for example, can you make the P2 square?
P2 square.
Yeah, by the combination of the STU.
Mm-hmm.
This is question.
So you were saying whether this set is equivalent to this set?
Not equivalent.
Yeah, I mean there are 3 in this, so obviously it's not.
Yeah.
Counting-wise, it's not.
Yeah. You must impose a lot of things like moment conservation and
Which I used.
and the on-shell condition to match the group.
Good. I think good. When the conservation is obviously true, so we are not gonna even violate that. On-shell condition, if you want to go wild, obviously you can just start using this bigger set. But eventually, we will float around the off-shell part of the momentum space, and then eventually we go to the on-shell regime to actually describe the physical amplitude. And all those other dependents will drop out, and the remaining only part will be only this set. So that's the sense, if you like. That's why we sort of organize physical amplitude only in terms of this. And then we will allow this to be off-shell value in the middle.
Then we cannot describe the off-shell amplitude via the STU, right?
We cannot describe off-shell amplitude as NTU. Was that your question?
Yeah.
We cannot describe off-shell.
Yeah, by analytic continuation of just STU.
Why? Sorry.
Because we cannot make P2 square.
PT squared.
to be n squared.
Okay, so that's when it is on shell. Sorry, what's the question?
P2 스퀘어가 n 스퀘어가 아니면 온쉘 조건을 포기하는 순간에 P2 스퀘어를 S랑 T랑 U의 컨비네이션으로만 갖다 맞출 수가 없잖아요. 그렇기 때문에 일반적으로 그냥 로렌츠 이베리언트한 P들의 컨비네이션을 ST U로만은 못 만들 텐데 온쉘 포인트에선 가능하겠죠.
Can we do the counting? So let's be general. I think I understand you, but let's consider like endpoint function. So suppose I have endpoint function. I have n external particles. So I can do 1, 2, which is 1 plus 2 square. I can do 1, 3, 3 square. And then I will have n minus 1 n. Square. Yeah? Okay. And I get entire this set, and I won't get explicit dependence of this set, right? And yes, I say
NDA 있습니다.
네. Okay. So that's what. So this is basically n choose 2. I'm not even imposing momentum conservation here. Okay. And what's the point here then? So these will be eventually just number.
Yeah.
Eventually this will be just number in the physical region that we will describe. Okay. And then you're saying that we cannot do. Okay. First, let's get to the analytic continuation story. But then you were saying that that continuation cannot be done if I put this on shell eventually. Was that your statement? How about we first go to the analytic continuation story and then you can ask your question in that context, because I need to understand that. Okay, so far what have I said was that we're gonna basically consider general 2-to-2 process, and we just understood the fact that even if we take this convention, going from the incoming particle to the outgoing antiparticle are related by switching P to minus P. So that's basically what I talked about. And then here, I just did exercise how to write that thing here, okay? So now, let's actually talk about Torsion property in a full, not completely full generality, but at least for the Q activity with the scalars. Okay, so now I want to deal with these three variables, modular expression. So for our 2-to-2 scattering, will be in general function of STU. Okay, so this is, in a sense, over complete set. Okay, and if you like, you may remember the fact that, for instance, when we talk about this, we needed only P, the size of the momentum, and then theta. The two variables you needed to specify the dynamics. But I'm using 3, so it's over complete set. Or if you remember this diagram, obviously you only needed the ET to specify. So again, in that case, these are still over complete set. But in general, here we are trying to be general, modulo the question we will see. So it's over complete set, but it's useful to use over complete set to see a relations among different processes. So let's actually jump in. So to do this, let's actually consider the following. So there's a one constraint S and T and U have to satisfy. So the condition is that the sum of all three satisfy the sum over mass squared. So this is true on shell. Okay? So sum of S and T and U is the same as sum over all the masses. So this is true again on shell. Obviously you will not see the mass. So you can show this by first looking at 2 times S plus T plus U. So I basically have S written in 2 different versions. So once like this, second is And then I'm gonna 2t, so t I'm writing once this way, and second this way. And then again, I have 2u, so once I'm writing this way, second this way. You see that the 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3 for everybody appears. So this will be equal to 3 times pi square. Okay? So 1, 2, 3 appears at least once in each disk floor. And then I will have 2 times pi, pj entire combination. Okay? So 2 times 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3, it appears. Okay, so that's that. On the other hand, P1, P2, P3, P4 satisfies momentum conservation. Right? And this is equal to 1. So now I have only 1 times pi squared. But this also has a 2 times entire combination of pi, pj. So if you subtract this, so this minus 0 is that. And then if you subtract, you are left with 2 times some over this. So hence this constraint. So what it means is that these variables overcomplete in the sense that it satisfies this one constraint equation. And geometrically, that constraint describes a plane. Equation. This is an equation for plane. Right? Why is that? So let me just draw. This is S, T, U. So in 3D, for instance, you may remember that equation for plane, so vector x living in the 3-dimensional Euclidean space, with respect to measured with respect to some fixed point A, and then the equation for plane is that if that thing is perpendicular to the normal vector, this is the equation for plane. Okay? So that equation can be viewed as 1, 1, 1 as a normal vector, S T U is equal to the constraint equation. So you should be able to just move in somewhere to rewrite this way. Okay? So therefore that equation is the same as talking about this plane, where starting from here, there's some normal vector sticking out of this plane along the 1, 1, 1 direction. I don't know if it looks like that. Does it look like that? You know what I'm saying? So it's that plane. And so this plane, oh, by the way, these variables, SPU variables, are known as Mandelstam variables. Mandelstam variables. Let me check the spell. Am I right? Oh. No, this was E. Mandelstam variables. And this plane that I draw, this plane is Mandelstam plane. And we want to define a unit vector. So you see, this line corresponds to S equal to 0. So entire physics living here, right? And then here T is 0. And then this is where U was 0. So this is U equal to 0. Okay? Now, intrinsically, if you want to talk about this Mandelstam plane, and then, therefore, with respect to origin, I can define a unit vector as US, what did I say? ES. And then, nobody complains. Very open-minded. So ET, and then EU. Okay? Again, this is over complete set of basis vectors. We only need the two to specify completely, but we are using it such that STU are treated as equally as possible. Okay? Good. So then, let's actually check the physical region. So where the physics lives. So now let's talk about physical reason. Let me spend 5 more minutes, okay? And then we can pick up again today at 5. So like I said, once again, the amplitude is a function of STU. Okay? And then we can consider a process such as this. For instance, this is T, time, not this T, time. Where S, which was by definition P12 square, is equal to ET squared. Suppose you had a physics where this sum captures the total energy. Okay? So total energy, so then we will name the channel, the name of the process or channel according to which variable plays the role of total energy, which the other ones play the role of a momentum transfer. Okay? So if I look at this way, then again I'm looking at this way. This variable, which will be now T, in this case P1 plus P3 square, this will play the role of momentum transfer. Okay? And then the other one will play the role of a cross momentum transfer. So in that process, in that channel, we will say, so that where the S plays the role of the total energy, the other two plays the role of a momentum transfer, we will call that channel, we will call that physical process in S channel process. Okay? Same diagram, exactly the same diagram. Now I can view time as this on the other hand. Now you see that 1 plus 3 plays the role of total energy. Okay? On the other hand, the 1 and 2 will play the role of one of the momentum transfer. So therefore, now if this plays the role of total energy, when U and S play the role of momentum transfer, we will call that process is in P-channel process. Okay, the idea is that we are keeping the block as it is. Okay, and then we look at this, that, and the other channel. Okay, and then we just check which variable play the role of total energy, which the other two play the role of a momentum transfer. And then obviously you can do the same thing. So if you have a U playing the role of total energy, and then the other two play the role of momentum transfer, then that process is in U channel. Okay, so it's a matter of taking this in and out, that's S, this to in and the other to out, that's T channel, this to in, the other to out, that's U channel process. Okay, now I'll draw one picture and then we will pick up that at 5. So here is my I'll just draw a big version of that. So that's where S equals to 0. And then this is where T grows. This is T equal to 0. And this is U. Okay? And let's check the S channel. So S channel obviously is this. So S P1 plus P2 square. Now you can look at it. So this will be E1 plus E2 square, and this is equal or greater than just picking up the mass of this thing. So for now, let me take the case where all the masses are equal. So this is the 4m squared. Okay, I'm taking all the masses are equal, all 4 particles. So in order for the S channel process to be in the physical region, the S variable should be equal or greater than 4m squared. Okay? Now you can check obviously T and U And then this gets saturated as T goes to 0, as U goes to 0. Okay? Meaning you just for this particle, nothing happens, no exchange of momentum. That's when you actually saturate this 4m squared. So when T is 0, what it should be, remember, this should be equal or less than 0. This should be equal or less than 0. So T is equal, this is positive T, negative T. This is U, positive, negative. This is U. This is U less than 0. This is T less than 0. And then when they both are equal to 0, this is when S becomes exactly 4m squared, and then in general, this is equal or greater than 0. So that is the this corresponds to S channel region in momentum space. Okay, in this Mandelstam plane. You can do the same thing. So let's pick the T. So when T is equal to greater than 4m squared, but S should be negative, U to be negative. So this corresponds to T channel. And then likewise, this is U channel. So this is where 4 processes live, or physical processes live. Okay, so I should stop here, but we will resume our discussion from here and then finish up the CP field areas and so on. Okay, at 5. Right, thanks. I'll see you at 5.